Okay, this problem, there's a lot going on here. So little by little. First thing is we have this object in space. Object 1, it has positive 3 microcoulombs and a certain mass of 0.0025 kilograms. What is the electric potential at point P due to that? Electric potential is right here. V is the symbol for electric potential. That's voltage. Better way to write this equation, V equals KQ over R. So for A, V equals KQ over R. K is 9 times 10 to the ninth Newton meters squared per Coulomb squared. Q is, what the heck is Q? 3 times 10 to the minus 6 coulombs. And R is 0.3 meters. Not squared. Important to recognize it's not squared. So you do some arithmetic. All right. 9 second E. 9 times 3 second E minus 6 equals that, divided by 0.3. Now we get 90,000 volts. 9 times 10 to the 4 volts. That's for part A. For part B, little unfair of me to ask you this right now. This equation, this thought is coming up in the next couple of slides. But how much work must be done to bring some other charge to this point? Over here is the equation. Change in energy equals, sometimes this is called electrical work. Change in energy equals Q delta V. We just figured out the delta V at that point, right? It's from infinity to there. So for B, we're going to go how much work or how much energy is spent. Delta U equals Q delta V. Q is the charge of the second object, 1 microcoulomb. 1 times 10 to the minus 6 coulombs multiplied by the change in voltage. It went from forever away, essentially a 0, to 90,000 volts. 9 times 10 to the 4 volts. So you get a delta U equals 9 times 10 to the minus 2 joules. That's B. C, what's the magnitude of the electrostatic force between them? The electrostatic force. I don't have this equation up there, but you probably remember it. It's so close to the gravitational force equation. Fe equals K Q1 Q2 over R. I like big multiplier. R squared. So now plugging in the numbers we know, 9 times 10 to the ninth multiplied by Q1 was 3 microcoulombs. Charge 2 was 1 microcoulomb. And the separation between them is 0.3 meters squared. Right? Plug and chug, do the math. 9 second E 9 times 3 second E negative 6 times 1 second E negative 6 gives us 27,000. 27,000 divided by 0.3 squared, or 0.09. Why do I feel like I missed something somewhere? Should be like 9 second E. That number doesn't make sense. 9 second E times 3 second E negative 6 equals that. Times 1 second E negative 6 equals that. Point. There we go. Forgot a positive. Be careful with your calculators there, but good to recognize problems. That divided by 0.3 squared gives us 0.3 newtons. All right. D, electric field. In the center, kind of an interesting point here. The E in the center here, there's going to be an electric field from object 1 that way. And then there's going to be an electric field from object 2 that way, right? Out from positives. They're both positive. So that whatever it is, we're going to do E from 1, E from 2, and the distance for each of these things is going to be 0.15 meters. All right, so as we're keeping our stuff, the E at the center is going to be the electric field from 1 plus the electric field from 2. All right, electric field, KQ over R squared, plus the other one, this would be K1, this could be K2, R squared. 9 times 10 to the 9th times 3 microcoulombs over 0.15 meters squared, plus 9 times 10 to the 9th, 1 microcoulomb over 0.15 meters squared. So we get here 9 second E, 9 times 3 second E minus 6 divided by 0.15 squared. So here we're going to get 1.2 times 10 to the 1, 2, 3, times 10 to the 6th newtons per coulomb. Here, 9 second E, 9 times 1 second E negative 6 divided by 0.15 squared. Four times 10 to the 5th newtons per coulomb. But here's the thing, remember, from E2, that's that direction. From E1, it's that direction. So this is like really adding a negative. So we come up from this number minus the other number, which is going to be 8 times 10 to the 5th newtons per coulomb. That's for D. The last problem, what's going to be the speed of the object when the objects are very far apart? Again, slightly unfair of me to ask you this about energy, but the energy is going to be the same. The energy lost, this energy lost, will be equal to the kinetic energy gained. Okay, so we're going to go with 0.09 joules is going to go to each particle, right? Both particles, KE of 1 and the KE of 2. Because they have the same mass, it gets distributed the same. 0.09 joules equals 1/2 mv squared plus 1/2 mv squared. It's the same exact m's. So basically 0.09 joules equals mv squared. 0.09 joules divided by 0.0025 kilograms equals v squared. V equals, do this math, 0.09 divided by 0.0025 equals 36. Square root of that, square root of 36 is 6 meters per second. And that's the problem.